Hello, everyone. Thank you for letting me speak to you today. My name is Josh Lepawsky. I'm a professor of geography at Memorial University, and I am going to talk to you about some ongoing research I'm doing about the relationship between climate change, water stress, and semiconductor manufacturing. Principally, I'm interested in what the unfolding climate emergency over the next coming decades might mean for the manufacturing of semiconductors. So what I'm going to talk to you in the next just few minutes is divided into three parts. I'm going to talk to you a little bit about what motivates the research, some findings, and then try to quickly draw out some broader significance for the issue of climate change induced water stress and future semiconductor supply chain risk. So first, a little bit about what's motivating the research. I have been interested for some time in the environmental implications of electronics broadly conceived, and turning my attention increasingly upstream, as it were, toward the the environmental implications of manufacturing has been a big part of what I'm doing. And more recently, I've become interested in how a changing environment may indeed impact manufacturing of electronics. Part of that motivation comes from something I noticed as the so-called chip wars, as they've been described in a number of venues, have been sort of framed. And a lot of that framing has been sort of classic geopolitical issues of interstate rivalry. You certainly see that in Chris Miller's book, Chip War, but you also see it in policy statements like the Chips for America document, as well as in recent war game scenarios when the chips are down. And those various publications pay a lot of attention to, as I say, to interstate rivalry. But when you look at any other factors that might impact semiconductor manufacturing, it's notable that in all of those sources, there is exactly zero references to climate change, which is quite something when one considers how important water is to various stages in the manufacturing of electronics, but in particular in the manufacturing of semiconductors. So I wanted to dig into this issue a little bit and try to understand how future climate change scenarios may impact on semiconductor manufacturing and supply chains. So this is some research that is very, very fresh. I hope it will be coming out soon. I just recently received a revise and resubmit on the manuscript that does this analysis, and I'm going to try and give you a high-level overview of the paper, and if anyone is interested in the issues that I'm talking about, please get in touch and I'd be happy to send you a draft. So a little bit about methods used in the paper. There's a great deal of detail here, but in principle, it's a relatively straightforward set of geographic methods, simply overlaying the location of fabs or fabrication, semiconductor fabrication sites over a global model of water stress risk. The location of fabs, cartoonishly depicted there in the gray with the square with the green dots. Those data come from a couple of different sources, a trade association database that covers 1,300 or so individual locations at the street address level and claims to be at or near 100% coverage for all fabrication sites globally, as well as some data from lent to me by Professor Henry Young at the Global Production Network at National University of Singapore organization or institute. So my thanks to Dr. Young for sharing his data with me. The water stress risk is a publicly available global water stress model from WRI, World Resources Institute. The model is called Aqueduct 3.0. And so the basic method was simply to overlay these sources of data with one another and see how those overlays line up under two different years, 2030, 2040, and in each of those years under three different climate change scenarios that are available in the Aqueduct database. Very simply, this is an optimistic scenario for climate change, a BAU or business as usual, and a pessimistic scenario. In other words, optimistic, things go relatively well for climate change, business as usual, things carry on more or less as they are going today, and pessimistic being that considerably more warming occurs. So let's dig in a little bit to the findings. So first thing to notice is that under these 6 climate scenarios, optimistic, business as usual, and pessimistic for 2 years, 2030 and 2040, that when we look at the differences between the most near-term water stress scenarios, the optimistic of 2030, and the most far-term and pessimistic scenarios, that there are not huge differences between these scenarios. So just to say a little bit about what these circles are showing, they're color-coded to the classification of water stress risk, low being low water stress risk, extremely high being extremely high water stress risk. And the size of each of the circles is just proportional to the count of fabrication facilities in each of those categories globally. So there are differences, but they are not massive between the most near-term and optimistic and far-term and pessimistic scenarios. But what is important, in my view, to understand is that under any of these 6 climate change scenarios, at least 40% of all fabrication facilities are located in watersheds that are projected to be either high or extremely high water stress risk in 2030 and in 2040. Now that's 40% is very substantial, and I'm going to talk a little bit in a moment about why those aggregate results are important, but also why some of the details matter as well. So my apologies that my image is cutting off the legend a little bit on the left there, but this is simply showing the global results for the location of watersheds classified into those water stress risk categories. So a light blue is a low stress and a dark red is an extremely high water stress risk. The percentages simply refer to the percentages of all surface and groundwater that is being extracted. So in the low water stress risk watersheds, less than 10% of available water is being extracted for all uses, including semiconductor manufacturing. And in the red zones, greater than 80% of all available surface and groundwater is being extracted for use, including, again, semiconductor manufacturing. Now, if we look at the center projection, the center globe towards the top, the fab locations are depicted by the green dots. You can see that many of them appear in Northeast Asia, in China, that are categorized as extremely high risk. There are so many on the islands of Japan that they actually sort of cover up the islands there, but many of them are in high risk zones as well. If we turn our attention down to the bottom left, you'll note that many of the fabrication facilities in the United States also occur in high or extremely high water stress risk regions for the 2030 business as usual scenario. And over on the bottom right, we can see Europe, a bit more of a mixed picture, but also many located in high or extremely high risk zones. Now, if your impression is that many of these fabrication facilities are depicted or located in high or extremely high water stress risk zones. You are correct. So let's look a little bit at the significance. So first, when we look at all existing facilities, and again, this is about 1,300 or so total facilities, under any of the 6 climate scenarios investigated here for 2030 or 2040, at least 40% of all existing facilities exist in watersheds that are projected to be high or extremely high water stress risk. I went a little bit further with the database and have been collecting information from publicly available sources about new facilities that have been that are under construction and their locations. When you look at just under construction, anywhere between 24 and 40% of those that are currently under construction are projected to be in high or extremely high water stress risk watersheds in 2030 or 2040, depending on the climate change scenario that you are looking at. And indeed, all of those that have been announced but not yet actually begun construction, they have a location announced, but they haven't broken ground. Then anywhere between 40 and 49% are anticipated to be in high or extremely high water stress risk watersheds. Now, those aggregate results, I think, are important in their own right, since they're telling us that a sizable proportion of all facilities are going to be in the highest risk categories. But what's also important to look at is how those facilities are networked together. So this is a somewhat complex diagram, I will admit. The outer circle, the outer ring of nodes is depicting actual fabrication facilities that are known to supply actual manufacturers, which are represented in the inner ring of circles there. So think of those arrows as flow lines of semiconductors from a supplier to a customer. And the outer ring of suppliers is color-coded based on their location in the water, the water risk category, where they are actually located on the globe. So you'll note, for example, that only one supplier is located in a low risk zone. All others are low, medium, medium high, high, or extremely high. But looking at these connections through this topological network starts to tell us some important information. And that is that not all companies are situated in the same way within these supply chain networks. So in at the companies that are circled with the dashes there, you'll see there are significant differences between them in terms of those who are supplied by suppliers who are almost all in extremely high risk water stress watersheds versus one which, just as an example, you see towards the top left of the diagram, that is supplied mostly by suppliers in the low medium category. Now, as I say, these are actual facilities with known supplier-buyer relationships. This is a subset of the overall data, but it starts to point us to real pinch points in actually existing supply chains as they relate to future climate change scenarios. So some of those actual facilities, of course, are located in places like Taiwan, which, as I'm sure many are familiar with, supplies roughly 90% of the highest end chips, and it is already experiencing very high water stress scenarios. And excuse me, this has made its way into recent reportage on the issue. We have heard perhaps of things like the water energy nexus, and that certainly is important in terms of the supply of energy to, for example, manufacturing. But one of the sort of growing implications that this reportage points to is that new conflicts are emerging where drought in Taiwan is pitting semiconductor manufacturing against agricultural production. And indeed, you can see that in Taiwan's exports of agricultural products to the rest of the world, which is depicted in the top right there. So just a measure over time from 2006 to 2022, the total cereals exports in kilograms over time. Now, Taiwan represents, a relatively wealthy region, which is able to overcome perhaps, domestic food supply issues by reducing exports. But of course, that has knock-on effects to those who were purchasing those exports. But also in a place like Taiwan, things like food security are tightly linked to issues of national sovereignty. So we're getting very much into social implications of climate change as they relate to semiconductor manufacturing, not simply the, if you will, the physics of water availability or scarcity. So we can, as many authors have, add to the water energy nexus, the water energy food nexus. And I would like to suggest that perhaps we also need to think about how computation is linked to these other issues, not just in the need for energy and water to run computational systems like data centers or what have you once they already exist, but of course, the availability of water and energy for the very making, the manufacturing of the hardware of computation, on which, of course, all software is dependent. Last point is simply to draw this into a broader frame. And to do that, just quickly draw to a recent publication from Cory Doctorow, a journalist, researcher, commenter on tech, who argues in his most recent book, How to Seize the Means of Computation, that if we someday triumph over labor exploitation, gender discrimination, and violence, colonialism, and racism, and snatch a habitable planet from the jaws of extractive capitalism, it will be thanks to technologically enabled organizing. So he's making this argument that a digital future isn't more important than all of those other fights, but he is arguing that digital technology is foundational to all of those other fights, saying tech is the terrain on which our future fights will be fought. Now, I remain a little bit agnostic, perhaps skeptical about that. But if this is true, then we must be thinking about how the environmental implications of manufacturing and the implications of a changing environment impact the manufacturing of the hardware that that technical terrain depends on for its existence.